10.1.4 Optimum Problems. So previously we learned that fx is maximum when the first derivative of fx is equal to 0 and the second derivative of fx is less than 0. And we also learned that fx is minimum when the first derivative of fx is equal to 0 and the second derivative of fx is greater than 0. So in this part of the chapter, we're going to deal with optimization problems. It normally involves problems of designing a container. So in designing that container, we need to determine, or we need to find what is the best dimensions that fits every side that can make the container holds as much volume as possible. Or at other times, we also need to determine the length of the sides so that we use the least amount of materials. So in order to solve the optimization problems, there are steps that we need to follow. The first one is to identify the variable to be maximized or minimized, say variable y. And number two, express y into a single variable function, say y equals fx. And then number three, we need to find the first derivative of fx, and then we need to find the value of x for when the first derivative of fx is equal to 0. Number four, we need to verify the solution of the first derivative of fx equals 0 by the second derivative. And then finally, we need to get the optimum value of y equals fx if it is required. Now we're going to try some example. So let's have a look at example 4, question number 1 on the lecture notes. An open top box is to be made by cutting small congruent squares from the corners of a 12 cm by 12 cm sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? So in this case, we need to determine the value of x, which is the dimension for the sides of the box, so that the box can hold as much as possible, or in other words, so that the box has the most volume. So this is how the box looks like when the sides of the tin are folded up. We can see here that the box has the dimensions of 12 minus 2x times 12 minus 2x times x. So because we want to find the maximum volume, we need to construct the equation for volume, which is V equals 12 minus 2x times 12 minus 2x times x. So that gives us 144 minus 48x plus 4x squared, and then all together multiplied by x. So finally V is equal to 4x cubed minus 48x squared plus 144x. So since we want to maximize v with respect to x, we need to find the first derivative of v with respect to x, which is dv dx. So dv dx is equal to 12x squared minus 96x plus 144. And for maximum value of v, dv dx is equal to 0. So when dx is equal to 0, 12x squared minus 96x plus 144 is equal to 0. Then solving that will give us the values of x that we need. So first we need to simplify. X squared minus 8x plus 12 equals 0. Then factorize. We get x minus 2, x minus 6. So finally we get that x is equal to 2, x is equal to 6. So from these two values of x, they could be the ones that give the box the maximum value, or they can also be the one that gives the box the minimum volume. So in order to verify that, we need to use the second derivative test. So first we need to find the second derivative of v with respect to x. So is equal to 24x minus 96. Then we take the value of x equal to 2. When x is equal to 2, the second derivative is equal to 24 times 2 minus 96 equals negative 48, which is which is less than 0. So we can say that it gives the maximum volume for the box. Otherwise, we should also test for x equals 6. So the second derivative for when x is equal to 6 is equal to 24 times 6 minus 96, which is equal to 48, which is greater than 0. So for x equals 6, we can say that it gives the minimum volume for the box. So in conclusion, we can say that the square cuts should be 2 centimeter by 2 centimeter. So that's all for example 4, question number 1.